Welcome to today's paper reading. Today's paper is titled, Knowledge-Enhanced Visual Language Pre-Training for Computational Pathology. This paper was published on AR14 by Zhou and colleagues from Shanghai Artificial Intelligence Laboratory and Shanghai Jiaotong University. In this paper, the authors addressed the challenge of visual representation learning in computational pathology. They introduce a pathology knowledge tree, which is a comprehensive structured knowledge base containing 50,470 attributes for 4,718 diseases across 32 human tissues. This is the first of its kind in the field. The authors also develop a knowledge-enhanced visual language pre-training approach. This approach involves projecting pathology-specific knowledge into a latent embedding space using a language model, which then guides the visual representation learning process. To validate their approach, the authors conduct extensive experiments, demonstrating significant improvements in various downstream tasks such as cross-modal retrieval, zero-shot classification on pathology patches, and zero-shot tumor subtyping on whole slide images. Pathology diagnosis is currently considered the golden standard for examining various diseases in clinical applications, particularly in the diagnosis of neoplasm. Over the last decade, the advancement of deep learning and computer vision has significantly boosted the development of computational pathology. This includes approaches using supervised learning and weakly supervised learning. Despite their promise, these methods are fundamentally limited by the scale of costly labels. Alternatively, self-supervised pre-training on numerous unlabeled pathological images has gained attention, yet it still requires supervised fine-tuning for practical applications. Recent studies on multimodal foundation models have shown improvements in downstream zero-shot tasks by aligning visual and language embedding spaces. However, representation learning in pathology requires significant expertise and domain knowledge. Existing works adopting simple contrastive learning on pathology image and caption pairs face challenges such as noisy and unstructured captions, and varying granularities of text that introduce ambiguities in alignment. Figure 1 illustrates the process of knowledge-enhanced pathology image-text alignment. The captions of pathology images collected from public websites are often unstructured and vary in granularity, leading to significant ambiguities in aligning these captions with the images. However, these ambiguities can be mitigated by using explicit disease attributes, which can be aligned with a structured pathology knowledge tree. For instance, LUSC and LUAD refer to lung squamous cell carcinoma and lung adenocarcinoma, respectively. In vision language pre-training, VLP, current approaches are divided into two-stream methods, which use separate encoders for visual and textual data, and single-stream methods, which employ a cross-modal fusion encoder. In medical VLP, two-stream approaches are prevalent, but they often lack systematic medical knowledge, affecting diagnosis accuracy. In computational pathology, recent advancements include the PLIP model and the QUILT-1M dataset, which expand pathology data. Additionally, models like MI0 and CONC enhance transferability on whole slide images. Medical knowledge-enhanced learning leverages external knowledge to improve deep learning models. This can be done through model-based approaches, which design algorithms based on prior medical knowledge, or input-based methods, which use knowledge as external input. However, most current works focus on chest X-rays. Figure 2 illustrates the construction process of the pathology knowledge tree, PathKT. The base architecture for this tree is OncoTree, a tree structure cancer classification system. The construction begins by extracting tissue types, disease entities, and attributes from web-crawled pathological descriptions. These descriptions are then matched to OncoTree using UMLS CUIs based on tissue types and tumor types/subtypes. Non-tumor diseases are also added according to their tissue types. The final pathology knowledge tree integrates 4,718 diseases from 32 tissues, with each disease node containing various attributes such as synonyms, definitions, histological features, and cytological features. An example of a disease node in the tree is combined small cell lung cancer, CSCLC. The primary goal of this research is to enhance visual language representation learning by leveraging structured pathology knowledge. To achieve this, the authors construct a pathology knowledge tree, PathKT, which includes 50,470 informative attributes of 4,718 diseases across 32 human tissues. This structured knowledge is then encoded into an embedding space using a knowledge encoder trained with metric learning techniques, specifically employing the ADA-SP loss. Furthermore, the knowledge encoder is utilized to guide visual language pretraining, termed knowledge-enhanced pretraining, KP. This approach involves creating a visual language embedding space and optimizing an influency contrastive objective, along with incorporating knowledge distillation to maintain alignment between images and captions within the knowledge space. Figure 3 illustrates the process of knowledge encoder pretraining using metric learning. The figure shows N disease entities, each with K attributes such as synonyms, definitions, and pathology features, forming a mini-batch. These are fed into a knowledge encoder for pretraining. In the embedding space, different shapes represent the embeddings of attributes from various diseases. The goal is to increase the maximum positive attribute similarity, S+I, within a disease and decrease the maximal attribute similarity, S-I, between different diseases. The purple dashed arrow and circle highlight the minimal positive attribute similarity in the second class and the hypersphere it spans. Figure 4 illustrates the model architecture for pathology knowledge-enhanced pretraining. On the left, a projection head is added on top of the visual encoder to bridge the gap between the image and text encoder. The knowledge encoder remains frozen throughout the training stage, continuously distilling pathology knowledge to the learnable text encoder. This setup ensures that pathology images are aligned with their implicit disease labels, as indicated by dashed boxes in the right graph. This alignment is possible because the captions contain disease attributes that are already aligned with disease names or synonyms in the knowledge embedding space. In this section, we discuss the datasets used for training and evaluation. The PathKT dataset includes 4,718 disease nodes with 50,470 attributes. For pre-training, we use OpenPath with 138,874 image text pairs and Quilt1M with 576,608 pairs. The evaluation is conducted on 3 downstream tasks: retrieval, zero-shot patch classification, and zero-shot WSI tumor subtyping. For retrieval, we use recall at K. For zero-shot classification, we report weighted F1, WF1. For WSI tumor subtyping, we measure balanced accuracy at top K. In cross-modal retrieval, KP32, pre-trained on OpenPath, demonstrates superior performance over PLIP, particularly on the ArchPubMed and PathPair datasets, with a significant 3% increase in recall at 10. For disease retrieval, KP32 significantly outperforms both PLIP and Quilt1M, likely due to the quality of captions in Quilt1M and the knowledge encoder's ability to focus on key disease information. In zero-shot patch classification, KP32 also shows better performance compared to PLIP, with medical-specific initialization further enhancing results. Our approach is less sensitive to varying text prompts, as indicated by the shorter boxes in performance distribution. Table 1 presents a performance comparison of various models on 3 retrieval datasets. The models evaluated include PLIP, KP32, KP16, and QuiltNet, all of which were pre-trained on the OpenPath and Quilt1M datasets. The tasks involve image-to-text, I2T, and text-to-image, T2I, retrieval. The performance is measured using the recall at 10 and recall at 50 metrics, with bold fonts indicating the best performance in each category. Table 2 presents a performance comparison of disease retrieval across different models. The table highlights the metrics of recall at 10 and recall at 50 for both label-to-text, L2T, and image-to-label, I2L, tasks. Notably, the KP32 model demonstrates superior performance, outperforming both PLIP and QuiltNet significantly. This suggests that the knowledge encoder within KP32 effectively focuses on key disease information during caption encoding, thereby enhancing the alignment between images and their corresponding disease labels. Figure 5 presents a comparison of zero-shot patch classification performance among various models. The left subfigure illustrates the results of models pre-trained on OpenPath, while the right subfigure shows those pre-trained on Quilt1M. Notably, KP32, initialized with CLIP, VidB32, outperforms PLIP across all datasets, with a significant enhancement of 0.137 on the Bach dataset. Additionally, KP16, utilizing BioMed-CLIP, VidB16, further boosts performance, especially in datasets where medical-specific visual encoders are beneficial. The figure also indicates that KP variants are less sensitive to varying text prompts compared to PLIP, as evidenced by the shorter boxes representing their performance distributions. This robustness is further supported by the visualization of prompt embeddings provided in the supplementary materials. Figure 6 presents a performance comparison of tumor subtyping across TCG-BRCA, common, TCG-NSCLC, and TCG-RCC-WSIs. The figure illustrates the first, median, and third quartile of the performance distribution for each model, with scattered points representing outliers. Models compared include KP16 and KPCTP, both trained on OpenPath, with visual encoders initialized by BioMed-CLIP and CTransPath, respectively. Additionally, Mi0Bio and Mi0Pub, variants of Mi0 with different text encoder initializations, are also featured, with their visual encoders initialized by CTransPath. Notably, Mi0 leverages in-house pathology reports for pre-training its text encoders. The results indicate that KP16 and KPCTP outperform other models across all datasets, demonstrating the effectiveness of the approach. Table 3 presents a performance comparison of tumor subtyping across 6 BRCA subtypes, distinguishing between common and rare cancers. The table highlights the best-performing models using bold fonts. Key findings include KP16's superior performance over PLIP and QuiltNet, KPCTP's dominance over Mi0Bio, and Mi0Pub's comparable performance to KPCTP. These results underscore the effectiveness of the KP models in tumor subtyping tasks, particularly in rare cancer identification. Table 4 presents the results of an ablation study focusing on the impact of model architecture and initialization. The study evaluates different configurations of visual and text initialization, knowledge metric initialization, and loss functions. Key findings include that the visual projection head significantly enhances zero-shot classification performance. The use of a pre-trained knowledge encoder consistently improves performance across various tasks, and freezing the knowledge branch further enhances performance in zero-shot classification and disease retrieval tasks. These results underscore the importance of specific architectural choices and initialization strategies in achieving optimal performance in visual language pre-training for pathology. In this paper, the authors addressed the challenge of knowledge-enhanced visual language pre-training in computational pathology. They first create a pathology knowledge tree that incorporates the essential attributes of diseases requiring pathological diagnosis. The authors then introduce a novel knowledge encoding method using metric learning to model structured pathological knowledge. Guided by the pre-trained knowledge encoder, they perform extensive visual language pre-training on pathology image caption pairs. To validate their approach, the authors evaluate the pre-trained VLP models on 3 downstream tasks: retrieval, zero-shot classification on patch-level pathology images, and zero-shot tumor subtyping on pathology WSIs. The quantitative results show that pathology knowledge significantly enhances performance across various tasks. This research is made possible by the generous support of 2 key funding sources. The first is the National Key R&D Program of China, which has provided crucial funding under the project number 2022 ZD0160702. The second is the China Postdoctoral Science Foundation, which has also contributed significantly to this work through their support, identified by the certificate number 2023 M741850. These funding bodies have played a vital role in enabling the research presented in this paper. Thank you for watching.